Alright, so this is the review video for Chemistry 103. Remember that this is a phase diagram, so you have solid, liquid, and gas. Notice that this one looks a little bit different, it's shaped a little bit different. That's fine. It's just for something other than H2O. But it's still solid, liquid, gas. So if we're talking about point X, that is a solid. If we're talking about point O, what is that? Alright, it's a gas. If we're talking about a point really close to the line, it's on this side of the line. It's still a liquid. Okay. Now, if you are directly on the line, we say that you're at equilibrium between liquid and gas. Okay, so some of your atoms or molecules might be going into the liquid phase, and some of them might be going into the gaseous phase. You're at equilibrium. This is called the critical point. This is called the triple point. You don't need to know what those are. You just need to know solid, liquid, gas. Okay? And, yeah. Alright, determine the molecular formula of a compound. Now, we've done this back a while, like third quarter, I think. Determine the molecular formula of a compound. The empirical formula of a compound of boron and hydrogen is BH3. Now remember, that's the reduced form of it. Okay? Its molar mass is 27.7. Alright? Grams per mole. Determine the molecular formula of the compound. So first we're going to list our knowns and unknowns. Alright? We know that the empirical formula is BH3. And we know that the molar mass is 27.7 grams per mole. Alright, that's of the formula we're trying to find. The mass of that formula is 27.7. And what we want to know is the molecular formula of the compound that has a molar mass of 27.7. Okay? So the first thing we're going to do is calculate the empirical formula mass. So we're going to find the mass of BH3. Okay? And so we look at the periodic table and we find the mass of boron, we find the mass of hydrogen, and it's 13.84. Okay? And then we're going to calculate the ratio of molar mass over the EFM, or the empirical formula mass. So molar mass, which is 27.7, divided by the empirical formula mass, which is 13.84. And when we divide those, we get 2. Okay? So the last step is we're going to take that empirical formula of BH3, multiply it by 2, and this is like the distributive property. And so we know that the molecular formula of the compound of boron and hydrogen that has a mass of 27.7 is B2H6. Alright, so that would be your final answer right there. Alright. Alright, on this one, we have 2 moles of sulfur dioxide plus 1 mole of oxygen gas produce 2 moles of sulfur trioxide or sulfite. Alright, and we can go the other way. The 2 moles of sulfite produce oxygen gas and 2 moles of sulfur dioxide. So then we might ask ourselves, if I add SO2 and O2, what will happen? Well, you think, and then we'll talk. Okay? So if we add SO2 and O2, those are reactants, that's going to cause it to shift towards the products. Okay? It's going to shift towards the right. Alright? If SO3 is removed, okay, if there's less SO3, again, it's going to shift towards the right because it's got to make more products. Okay, so if SO3 is added, the equilibrium will shift too. Well, if I add a product, SO3 is a product, it's going to shift this way. If SO2 and O2 are removed, the equilibrium will shift blank. All right, pause the video, think about it. All right, SO2 and O2 are reactants. So if I remove reactants, I'm going to shift to the left in order to replace those reactants. All right, shifting to the left will cause blank to be formed. Pause and think about it. All right, the reactants are on the left and the products are on the right. So shifting to the left will cause reactants to be formed. So in this case, that would be SO2 and O2. Shifting to the right means products would be formed. All right? So if you need to write that down, pause the video. All right. Now this is some new stuff, like new stuff. Molarity is just a ratio of the moles of the solute divided by the liters of the solution. Okay, so how would you calculate this? Well, here's an example from the textbook. A solution is prepared by dissolving 42.23 grams of ammonium chloride into enough water to make 500 milliliters of solution. Calculate its molarity. Right? So we know the mass of the ammonium chloride. We know the molar mass of ammonium chloride, and if we don't know that, we look at the periodic table and we calculate it. Nitrogen plus 4 hydrogens plus 1 chlorine atom, 53.5. We know the volume is 500 milliliters, but we're going to need to convert that to liters by dividing by 1,000. All right, and we want to know the molarity. All right, this is an important step. If you don't do this, your numbers will be wrong. Okay, so this is in liters, so this has to be in liters. The mass of ammonium chloride is first converted to moles, then the molarity is calculated by dividing by the liters. So we take the 42.23 grams that we have, and we divide that by the 53.5 grams in 1 mole. And that tells us that we have 0.7893 moles. Okay? Think of it this way. If you had 6 eggs, you would divide that by 12 to find out you had 0.5 dozen. Right? So that's all we did there. And so then we take the 0.7893 moles of ammonium chloride and divide it by 0.5000 liters, and that equals 1.579 molarity for the solution. All right, so that's how you calculate molarity. Now, the actual problem you would have looks like this, but you have to be able to calculate molarity to do it. All right. In a titration of sulfuric acid against sodium hydroxide, so basically with a titration, you have a known amount of base in this scenario and an unknown molarity of acid, and you use one to figure out the other. Okay, that's what a titration does. And so we have sulfuric acid and sodium hydroxide. We know that 32.20 milliliters of 0.25 molar sodium hydroxide is required to neutralize 26.6 milliliters of H2SO4, which is sulfuric acid. All right, and we have to calculate the molarity of the sulfuric acid. So what we're going to do is we're going to look at the equation, right? And we're going to need that. First, determine the moles of NaOH in the reaction. All right, so to do that, we're going to take, we know that it is 0.25 molarity, right? So we're going to take those, that 0.25, we're going to multiply it by the number of liters, the 32.2. But look, this is milliliters. This has to be liters. So we had to convert that to 0.03220 liters. We multiply those, we get 8.05 times 10 to the negative third moles of sodium hydroxide. Now that we know how many moles of sodium hydroxide we had, we're going to multiply that by the mole ratio from the equations. You guys did this. This part you've done. Okay? So we're going to say, we look and we see there's 2 moles of NaOH for every 1 mole of H2SO4. So we multiply those and we're left with 4.03 times 10 to the negative third moles of sulfuric acid. So that's how many moles of sulfuric acid we used. Okay? Now we take those moles and we divide them by the number of liters of H2SO4 that we were given in the problem. Again, we had to convert it to liters. Okay? And we divide and we get 0.150 molar H2SO4. Right? It's not super complicated. It is new, and so I'll be kind with grading, but that is what you do. Okay. Here we have 3 different electron configurations, and we want to know how many valence electrons there are. Valence electrons are only in the outermost s and p orbitals. All right, so this one has 8, so it must be a noble gas. This one has 1. This one has 2. Okay, I know what you're thinking about, Mr. Furlow, there's a 3p6, but that's not the outermost. Okay, the 4s2 is the outermost. So there, the answers would be 8, 1, and 2. Here, the main thing you need to take away is that hydrogen bonds are particularly strong. Polar attractions can be strong. Covalent bonds and ionic bonds are both kind of strong. London dispersion forces are very weak intermolecular forces. Okay, London dispersion forces are very weak. All right, electronegativity is the measure of the tendency of an atom to attract a bonding pair of electrons. All right, and it increases from right to left, and it increases from bottom to top. Okay, and so increasing electronegativity. So we have lithium, and we have carbon, and we have fluorine. Fluorine is much more electronegative than lithium because it's a non-metal. It wants to gain electrons. Lithium is a metal. It wants to give away electrons. All right. By the same token, though, francium is very low electronegativity. It would be the lowest on the periodic table. Cesium would be a little bit higher, and sodium, even though it's low compared to a nonmetal, sodium would be higher than cesium and francium. Lithium would be higher than sodium. All right, and that's it. Hope this helps, and I'll see you tomorrow in class. Stay curious.